distribution of the sample means. Okay? Now up to now, I've given you this equation z equals x bar minus mu over sigma over the square root of n, right? And I've told you that this was going to come up eventually. Today's the day. Okay? So you should be well prepared for this, I hope. So what we're going to be talking about is what's called the central limit theorem. Okay, this is one of the two most important theorems in all of statistics. Okay, what it basically says is, regardless of the underlying population distribution, the sample means, the distribution of the sample means is normally distributed. Okay? So let me give you a for instance. So let's say that I wanted to simulate an IQ test scores with random numbers between 75 to 125. Okay? So I'm going to do that right now. You guys can follow along if you want, although obviously you'll get different numbers than I will. Okay? So I'm going to use the command equals rand between, and I'm going to pick 75, 125. Okay? Just like that. Now I'm going to copy this over 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then I'm going to copy it down 100 rows. Not too far. 100 rows. Okay? So these are just a bunch of random numbers. I don't want them to change, so I'm going to press Control C. I'm going to copy them. I'm going to paste special. I'm going to click on the 1, 2, 3. And now they're not going to change. Okay? So we've just got basically 900 random numbers here. Okay, let's pretend this represents a school, school of 900. Okay? So let's think about this for a minute. Okay? If we were to talk about this school, so I've got a school of 900 students here I just created. What would the distribution of these 900 numbers look like? If you were to draw a picture of them. What? Bell curve is the wrong answer. That's what I expected though. Okay? So remember at the beginning of the week, I told you there was a distribution that you were going to forget, and you've already forgotten it.
Oh,
The rectangle one, what's it called? Uniform distribution. So this is a uniform distribution. What does a uniform distribution look like? Somebody said it already. Looks like a rectangle. Okay? Which doesn't look like a bell curve at all, does it? Okay? So in this case, my rectangle is going to go from 75 to 125, right? Now, I'll bet you, without very much thought, you could tell me what you think the mean of this distribution should be. You would expect the mean to be about 100. You would be correct. Now, according to the central limit theorem, okay, it says regardless of the underlying distribution, the distribution of the sample means is normally distributed. Okay? So in this case, this does not look bell curved, does it? Not even close. Okay? What the central limit theorem says, well, if you were to find a bunch of x bars, okay, so this is your population mean mu. If you were to find a bunch of x bars, I'll put those in a different color. Your x bars would be normally distributed. Okay? So it doesn't, so according to the central limit theorem, it doesn't matter what your underlying distribution is. If you had a normal distribution, say the mean was 0, and then if you did your x bar distribution, it would also have a mean of 0. Or if it was skewed, sorry, that's not very skewed. If it was skewed to the right, let's say that was your mean, you would have a distribution of sample means that would be there, or if it was skewed to the left, or if it was crazy weird, something like that, maybe the mean would be here, you would have a sampling distribution of x bar that would be there. Okay? So this is a pretty cool theorem because what it tells us is, oh, and actually I left off a big F here. If your sample size is large enough. That was a big F. Okay? So then the next question is, how large is large enough? Right? So it often works when n is greater than or equal to 30. Now I'm going to emphasize often, and that doesn't mean always. Remember on your quiz today, how big was your sample size on number 1?
48.
It was 48 and it wasn't big enough. Okay? Remember also yesterday we did a QQ plot of something, now it should look like a 45-degree line, and we did it and it looked like this, right? That had an n equal to 100. Okay? So just because your sample size is 30, you don't assume, oh, it's a magic wand, central limit theorem always applies, okay? You still need to back it up. But it often works when your n is greater than 30. And I will add a qualifier on that. It often works on quantitative variables, okay? Let's talk about number 1 on the quiz today. Was that, what kind of distribution was that? Taylor and Josh know, because they got it right. What was it? It wasn't normal. It was a binomial, okay? So binomials, definitely this 30 rule doesn't work, because 48 was too small. And just because it's quantitative doesn't necessarily mean it will be normal either, but it often works. Okay, so you should verify that, okay? So I just know that a lot of people go, oh, 30 is good enough, okay? Not always good enough. Okay, so we've got this school of 900 here. So what I'd like to do, I'm going to insert a row, okay? And, why does this do this to me? Sometimes I hate this computer. What is it doing to me? Why do I have this stupid eraser here? Driving me crazy. Okay. It just did it again. I don't want the pen. Get away from me. Okay. Okay, so what I'd like to do is I'd like to find the x bar. Okay? So what I'm going to do, since these are just random numbers, I'm going to pretend this is a random sample of size, each row is a random sample of size 9. Okay? So in this case, I'm going to find the mean, curse Bill Gates, for using that wrong command, of the first row. So the first row works out to be 99.9, which is very close to my mean, by the way. I'm going to do this for all 100 rows. Okay. So you can see here 102, 96, 97, 100, 409, that was pretty high. 93, 90, that was pretty low. Okay, so we've got, yes?
Sorry, how do you make it so all your numbers don't change?
Okay, so copy the whole thing, copy the whole sheet,
Okay.
and then do a paste special. No, you didn't copy it. Paste special, click on the 1, 2, 3.
Oh, okay, thank you.
Okay? All right, so we've got some variation going on here, right? Okay, so it's not always equal to 100, but what the central limit theorem says, if you were to draw a histogram of that, it would look like a bell curve. And if we have time, I will do that later. Okay, so my question is, we can also figure out the population mean, right? How would I figure out the population mean? The mean of the entire population, right? All 900 students. Okay? So if I found, because that's nice, usually you don't know the population mean, but in this case you do because I've got it here. So the population mean works out to be about 100, which is about what I said it should be. Okay? Now let's do the mean of the means. Okay? So what I'm going to do is I'm going to take the mean of all 100 of my means. Now before I press enter, I'm going to ask you guys a question. Okay? Do you think that the mean of my means will be the same as the population mean, more or less? So who thinks it's going to be higher? 1, 2. Who thinks it's going to be lower? Nobody? 1. Who thinks it's going to be the same? 3, 4, 5, 6. Who didn't vote? Okay. People who didn't vote definitely got it wrong. Drum roll here. It's exactly the same. Is that not cool or what? Okay. So what that means is that x bar is what we say an unbiased estimator of the population mean in U. Okay? We nailed it. We got it exactly right. Okay? So that is a very cool thing.
Is that
okay?
always the case?
No, well, what do you mean is always the case? I did 100 samples here. This first one was 99.9. That's really close to 100. But some of these are off. 97, 104, 109. Okay? So I'm not going to hit the population mean every time. Okay? There's going to be some variation, which is why I have my bell curve here. But the distribution is unbiased. If I do this 100 times, I'm going to nail it. I nailed it. Okay? So the distribution is an unbiased estimator of mu. Okay? Very cool feature. And the cool thing about this is it doesn't matter that this is a uniform distribution, or this is skewed, or this is normal. It doesn't matter what the underlying distribution is. Your distribution of your sample means x bar is always, 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 always going to be normally distributed. Okay? Which is a very cool feature. Okay? That's why we love the central limit theorem so much. Okay? Now, let's figure out what would be the population standard deviation. Okay? How would I figure that out really quickly and easily? Standard deviation, and in this case I'm going to use the population command because I actually have all 900 of my data here, right? So I'm going to highlight all 900 students. Okay? I got value of 14.25. I was hoping that would actually be a little higher. Okay? All right, so now my question is, if I did the standard deviation of my means, okay, standard deviation of all of my means, okay, once again I'm going to ask the same question. I'm not going to press enter yet. Before I press enter, is my mean of standard deviation of my means going to be higher, lower, or exactly the same as my population standard deviation? Who says higher? Who says lower? 1, 2, who says 3, who says the same? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, drum roll clear. It's much lower. Okay? Now, I actually drew that on here. Some of you may have noticed that on the board. Notice my standard deviation of my sample mean is much smaller than my population in all cases, and even here. Okay? So the question is there a relationship between those two numbers? And according to the central limit theorem, it turns out there is. So the one thing that we can say is S, if I talk about my S as my standard deviation, S is a biased estimator of your standard deviation, okay? We're way off. We're off by almost 10 in that case, almost triple in this case, okay? So the relationship turns out to be, if you take the population standard deviation, and if you divide that by the square root of n, that becomes an unbiased estimator of your standard deviation of your sample means, okay? And so that's why we have this in your formula, okay? We want an unbiased estimator of the sample means, okay? Now you're familiar with the equation z equals x minus mu over sigma, and I've told you just use this one because they're so similar, okay? This is why we have the square root of n in there, okay? So if I take my population standard deviation, and if I divide it by the square root, so each row is a sample size of 9. So if I take this and I divide it by the square root of 9, okay, that's going to give me, these two values are pretty close. Okay, they're not exactly the same, but they're close. Okay, so that's why we want an unbiased estimator. We want this to be close, at least close to what, we want it to be a better representation of the standard deviation of the sample means. And that's why that is in the denominator instead of just plain old this. Okay? Does that make sense? Does it make you love the central limit theorem? Not yet, but you'll love it. Okay? Yes?
So why wouldn't you take the square root of 900?
Because my sample size is only 9.
Just your sample size. Okay.
So what I'm doing is I'm taking any one of these rows, okay? Because you're not going to sample all of them, okay? And the fact of the matter is, let me show you this really quickly, just in case you didn't believe me. I have this other spreadsheet that will make histograms quickly and easily. Right here, okay? So if you take this is pretty cool. If I paste special values, okay, so you can see, even though my underlying distribution is uniform, you can see that this looks pretty bell curved, right? So that's just my sample means there, okay? So that's an illustration of the central limit theorem. Once again, underlying doesn't matter. Sample means are normally distributed, usually when n is greater than 30. In our case, we got away with it with only 9. Okay? So, yeah, this is a rule of thumb. It's certainly not a law. Okay? All right, does that make sense? Okay, I know we're short on time. Let me just do one quick example that illustrates this here. Okay. The national average of weight gain for pregnant women is 30 pounds. Obstetrician in low income neighborhood has 35 patients and finds average weight gain is 36.2 pounds. look at that and say, well, that's only 6 pounds, but is that a significant difference? Okay? So we're gonna plug this into our formula here, z equals, before I do that. Okay, so when you're doing these problems, sometimes it's really good to emphasize. I'm gonna get really into notation here, okay? Your mu is your 30. Your x bar is your 36.2. Your n equals 35. And, oh, I forgot to give you your standard deviation. The standard deviation is 12.9 pounds. So that's going to be your sigma, is 12.9 pounds. Okay, so I'm going to use my z-score. It's going to equal my x bar minus my mean. I'm going to take that, I'm going to take the standard deviation, I'm going to divide that by the square root of my n. That's going to give me this divided by that. That's my z-score, okay? So essentially I've said these women are 2.84 standard deviations away from my mean. My p-value is going to be 1 minus my norm s dist. Like that. And it says that only happens about 0.2% of the time. So this kind of goes back with Marissa's homework question today. Would that be considered unusual? Yes. Her patients are gaining too much weight. They're going to have to stop eating at McDonald's or something like that. Okay? They're gaining too much weight for some reason. Okay? So yes, she should be concerned. Okay? All right. So homework or a quiz on Monday will be at 8.1. See y'all then.